So it might have occurred to you in the last video that when we were talking about the idea of systems of equations having a solution by looking for where the two lines actually intersected with each other. And perhaps you were thinking to yourself, well, is that the only possibility? Certainly, if we have two lines in the plane, and I'm going to draw a couple of pictures of lines right here. Let's say that I've got a linear function that looks kind of like this. Right? Oh, come on now, I want a line, not a hand-drawn thingy there. Get my eraser going here. Let's try that again. Let's say that I've got a line that goes like this. It's just passing through the plane here. Okay, so I've got line number 1. And then I've got line number 2, which I'll draw here in red. So let's say I've got another line goes like this here in the plane. Right? Something about like that. Right? What we see right here is that we have these two lines that intersect at a single point. Well, we need some terminology right here so that you are on board with it. When we have a single equation, we have a single solution, right? There's some point A, B that follows where these 2 points meet, right? When there's a single solution, we call that an independent system of equations. An independent system of equations is defined specifically, right, as when the system of equations intersect at exactly 1 point. So we only have 1 point. Well, is that the only possibility? Again, Professor Peoples, you're not answering the question. Well, let's try it out right here. Let's say we do have another line right here. Let's say that we have, this time I'm going to graph it in blue. We have a line that goes like this. Can you think of a situation in which we have another equation of a line, but there is no solution? Yeah, exactly. If you stopped and you thought about this one for a minute, you'd think, well, sure, what if I just put the line down here and made it parallel to the last guy, right? So everywhere these guys go, they have exactly the same slope, right? In this particular case, what would we say about this one? Well, where the first one was independent, right? In other words, the two equations were independent of one another. Independent here, right? One solution. In the second case, we're going to say that these two are called inconsistent, which means that there are no solutions, right? Is that possible? Sure it is, right? As long as the two lines are parallel. Right? So if we have a system of equations in two variables and the two never meet, well, sure enough, that's inconsistent. All right, so that's our second one right here, right? So this is our inconsistent system. What about that last one, dependent? What do you think that one means? Well, what's our third possibility? Well, if we think about our possibilities right here, make sure I've got a line here. One possibility was that the two lines meet in 1 point. One possibility is that they meet in no points. How about one more where the two lines meet at every point? What's that you say? Every point? Sure. What if we just have the same line that's expressed in two different ways? Right? So these two lines are said to be dependent. Right? So dependent means that we have two lines that intersect everywhere. So we would call this one a dependent system. Make my marker work here. Dependent. Right? So there are infinite number of solutions in this case, or what happens if they just happen to be exactly the same line, right? We know that there's more than one way to express the equation of a line, so it's possible that we get more than one solution if the two lines are just lying one on top of the other. So that's our third possibility. So a dependent system means there's an infinite number of solutions. Okay. The real question is, well, how do we know when that happens? Well, let's try this out. Let's do a little bit of graphing here and see what happens if we try it. So let's go to the next one here. All right. So let's say we're going to solve the following system of equations by graphing. Now, you should take a minute right here. I'm going to pause and allow you to draw this out for yourself so you can compare. So just pause the video for a moment. On a piece of graph paper, just try and graph these out. Okay, so hopefully you've done that. And here's my first equation when I graph it. I'm using my super duper machinery right here. That's what 2x minus y equals 3 looks like. And how about this one? What do you think is going to happen here? Let's try it out. Ah, one lies on top of the other, right? In this case, this is a dependent system. This is a dependent system. Right? In other words, it meets everywhere. Everywhere along this line is the same for both. Y equals 2x minus 3 happens to be just a different way of saying this. Now, when we get a solution like this, what we should do is we're going to say, well, what do the solutions look like? Well, at every point, right, we can kind of figure out what's going on right here, right? So, for example, let's just pick a point like this one right here at 3, right? If we put in 3, 2 times 3 minus 3 is 3. Right? That is a solution. How about right here at 0? Right? If we put in 0, what do we get right here for y? Well, 0 gives us negative 3. Right? So what's the relationship right here? Well, it turns out that any point along this graph that fits the pattern where for whatever value of x we put in, the y value is 2x minus 3, this is the way that we could express that particular kind of solution. All right, let's try it one more time. Let's say this time we're trying to solve a system of equations by graphing. Again, I'll pause and allow you to take a moment to do it. Okay, what did you come up with here? Well, let's take a look here, see what I have. Let's take this first equation and plot its graph. Ooh, boy, that's kind of zoomed in on, but all right, we'll deal with it. Let's take the second equation and let's check it out. Ooh, all right. Well, you know what's going on here, right? Sure. Sure enough, what happens is that these two equations are parallel to one another, right? So what do we call that one? Absolutely. We call this one an inconsistent system. There is no solution. So there is no point where these two will intersect with one another. Now, this is a fact that you might have observed that if you solved for y in the first equation and rewrote the two, you'd see something like two lines that have exactly the same slope. Substitution method in the next set of videos.